If I told you there was a plan to launch a spacecraft the size of an ocean liner that would weigh 130 times more than the space shuttle, could travel at unrivaled speed across our solar system, and was powered by riding on a series of pulses created by exploding thousands of miniature atomic bombs one after another behind the ship, you'd probably say that I've been reading far too many sci-fi books and watching films. However, in the 1950s and 60s, just such an idea was taken very seriously. Project Orion was a classified American project to harness the power of the atom to lift extreme payloads into Earth orbit and beyond. After the launch of Sputnik by the Soviet Union, the shock to the US establishment was so great that almost any idea to catch up and overtake them was up for grabs. The first calculations into nuclear pulse propulsion appeared in a 1947 memo co-written by the famous physicist Stanislav Ulam, who worked on early nuclear tests at the Los Alamos laboratory. His idea was to detonate a nuclear device in a combustion chamber and inject water as a propellant. By 1955, the concept had developed, and in a report co-authored by Ulam, set out a better model to propel a projectile by external detonation of nuclear bombs. The government research agency ARPA, the Advanced Research Projects Agency, gave a $1 million contract to the General Atomics Lab near San Diego to develop the idea into a working concept. General Atomics was set up after the Second World War to explore the peaceful way to use nuclear energy. The project was led by physicist Ted Taylor with a team of scientists, many who had worked on the hydrogen bomb, including Stanislav Ulam himself and the renowned British mathematician Freeman Dyson. Although these physicists enjoyed playing around with bombs, they also dreamed of using their discoveries for constructive and humanitarian purposes. Project Orion had obvious military uses, but the team focused their vision for travelling to the far reaches of the solar system, to transport a crew of hundreds of scientists to explore Mars, Venus and the moons of the gas giants Saturn and Jupiter. The concept was simple and based on technology which was readily available to the US military in the 1950s. A series of small nuclear bombs, each the equivalent of about 5 kilotons of TNT, would be ejected from the back of the ship at a rate of 2 to 4 per second. These bombs would be made to direct most of their energy towards the ship's 1,000-ton steel pusher plate, and it's these series of pulses which will propel the huge spaceship forward. To demonstrate the concept, a team at General Atomics built a 1 metre or 3 foot diameter model shaped like a bullet, which they then loaded with conventional explosive charges. Sure enough, the model cruised up into the sky, riding on a chain of explosions with surprising stability. According to the calculations, the forces on a full-sized Orion would be similar to around 2 to 4 G, which is comparable to a conventional rocket launch. Nuclear pulse rockets also offered some significant advantages for spacecraft design. With this kind of propulsion, it would not only be possible to build heavier spacecrafts, it would actually become an advantage to go big. The Orion spacecraft would already need to be heavy to absorb the forces of the nuclear pulse through its pusher plate and the giant shock absorbers. So rather than using lightweight composite materials like the Apollo spacecraft, the payload and living quarters of Orion could be made from ordinary steel. In the words of a physicist, Harris Mayer, it will become a project of standard engineering, like building the Brooklyn Bridge. The Orion spacecraft will be constructed in submarine shipyards and will be similar in many ways to nuclear submarines already being built by General Atomics' sister company General Dynamics. Both had to be able to support a crew for an extended trip and withstand pressure, the vacuum of space being less punishing than the compression of a deep-sea dive. Appropriately, the plan was to launch the Orion spaceship at sea, just like the concept of the Sea Dragon rocket, which was in development at the same time. Launching at sea removed the need for a huge launch pad and also avoided issues with deflection of debris during the first moments after launch. The sea launch of Orion would have been a spectacular sight. A succession of larger explosions, each brighter than the sun, lifting the giant spaceship up vertically above a series of fireball clouds. However, the General Atomics engineers faced unique and significant challenges, one of which was that the shock of each explosion could not be so large as to injure the human occupants or shake the craft apart. Freeman Dyson's calculations showed that it would take about 800 bombs to lift the Orion spacecraft into low Earth orbit, and many more for the interplanetary travel thereafter. The effect of these bombs exploding in the atmosphere would be a lot of nuclear fallout. Unless a solution could be found to clean up the radioactive debris, this was a major obstacle in the way of Project Orion becoming a reality. However, the high stakes of the Cold War pushed the development of the project towards potential military applications. Thomas Powers, second in command of the Strategic Air Command, reportedly said, "Whoever controls Orion will control the world." However, when President Kennedy was shown a model of a militarized Orion, complete with nuclear missiles and atomic cannons, as a monstrous orbital battleship, he was horrified. To Kennedy, the last thing the world needed was a huge nuclear weapons race in space. Orion had been touted as an alternative to the Saturn rocket for the moon missions, but NASA was a civilian and open organisation, and Orion was still a top-secret project under control of the US Air Force. In fact, many parts of the Orion project, like the construction of the small, cheap atomic bombs, are still highly classified so as to keep the technology from falling into the wrong hands. Public mood was also shifting against the emerging nuclear-powered future. Strontium-90, a byproduct of fission, had been detected in the milk and in babies' teeth. In the face of these health concerns and the global panic of the Cuban Missile Crisis, Kennedy signed the Partial Nuclear Test Ban Treaty in 1963. This ruled out all above-ground nuclear testing and effectively made Project Orion unworkable. To the scientists who had already spent 5 years working on the project, the technology was too powerful to ignore. After all, no other technology offered the same potential for taking large payloads to other planets. In 1964, NASA considered using a smaller nuclear pulse rocket that could be launched aboard a Saturn V and then assembled in orbit. This would be an 8-man crew to go to Mars or a 20-man crew to go to Jupiter. However, by this time the space race was fully focused on the moon landings, and the job didn't need a rocket anywhere near as powerful as Orion. Finally, in 1964, the project was terminated. Chemical rockets, inefficient but relatively safe, would be the only way of getting off the Earth. Since Project Orion, the principles of nuclear pulsed propulsion have been revisited many times. In 1968, Freeman Dyson wrote a paper entitled Interstellar Transport, in which he calculated that a version of the Orion ship could travel to Alpha Centauri, our nearest star, at 10% of the speed of light, taking 44 years to arrive. 5 years after Dyson's paper, the British Interplanetary Society conducted a study into the potential mission using a nuclear pulse propulsion system. Known as Project Daedalus, the concept envisioned building a 190 metre or 620 foot long robotic spacecraft in Earth orbit, which would then travel to Jupiter to scoop up 50,000 tonnes of helium-3 from the gas giant's atmosphere. The fueled Daedalus would then accelerate out of the solar system, reaching 12% of the speed of light on a 50-year voyage to Barnard's star. However, unlike Project Orion, Daedalus relied upon nuclear fusion, a technology that is still out of reach. According to George Dyson, son of Freeman Dyson, a team at NASA have a contingency plan to put nuclear pulse technology into action if a large asteroid is discovered on a collision course with Earth. In such a situation, a version of Project Orion might be our only chance to deflect the asteroid earlier and with greater velocity than we could with a conventional spacecraft. With the cancellation of NASA's asteroid redirect mission in President Trump's budget, a version of Project Orion could still appear if the need arose at some future point to change the course of human history. So thanks for watching, and I'd just like to say that this episode's shirt was the Peacock fan shirt in yellow by Madcap England and is available from Atom Retro with worldwide shipping from here in the UK. We also have the Curious Droid Facebook page, the link is in the channel page, and I'd also like to thank all of our patrons for their ongoing support, and if you would like to support us, please visit our Patreon page in the link. So as always, thanks for watching, and please subscribe, rate and share.